Hi everyone, we are on to basically problem 3 in our practice exam. So I want to keep working with vanadium, but now I want to make a diffusion couple where I put vanadium on one side, I put hafnium on the other side, and you can see in the phase diagram in question 4, I'm going to set my diffusion couple, and then both are going to be 0.02 meters, so 0.02 meters, basically now I'm asked to draw the concentration profile as a function of distance, so concentration, distance, for several different times. So at time t equals 0, for both of them, they're just going to be kind of 1 and then flat. Probably shouldn't have drawn that, but anyways, you can kind of see the purpose here. Now, if we look at this phase diagram, I can see below, I've already written on it, that vanadium, I can put more hafnium into my vanadium phase. So hafnium is more soluble in vanadium, and we could tell that by our maximum solubility here versus our small maximum solubility right here. So my hafnium is more soluble in vanadium, thus my diffusivity of hafnium is G of HF is greater than diffusivity of vanadium. So if I draw another curve, so let's just keep looking at hafnium. So at another time for hafnium, it's still going to be 1 here, but then I'm going to start to diffuse in, and then for my other time, it's going to be like that. Now, for my vanadium, it'll be like this, and then it'll be like still a little bit like this, and a little bit increasing. But anyways, nothing compared to hafnium. So, fantastic. Write out the PDE and ODE must solve to find these concentration profiles. So 0.02, that's still a pretty large distance, so I'm going to make my semi-infinite solution. So this solution is valid as long as 10 square root dt, the length of my material, is greater than this. So if I'm looking at here, I'm going to set this as my x equals 0. So if I'm looking at the concentration of vanadium at eta equals, this is infinity, this is minus infinity. At infinity, it's going to be equal to 0. At minus infinity, it's going to be equal to 1. And vice versa for hafnium. So my PDE, read the question, is this, b squared c x squared. My ODE is b squared c squared plus 2 eta c eta equals 0. ODE, PDE. So those are my ODEs, those are my PDEs, there's my boundary condition. When is my solution valid? As long as this assumption is met. Fantastic. So, draw the fluxes in the diffusion couple. Magnitude. How did you determine the direction? What about them? So, we know here now, I'm going to erase this, that my diffusivity of hafnium is greater than that for vanadium. So, my hafnium is going to diffuse this way, so my flux is larger because my diffusivity is larger. So, hafnium. Vanadium is going to go in this direction. C vanadium. And then also the flux of vacancies now in the C frame is going to be equal. Because I need the flux of this, this, and this to all be equal to 0 in the C frame. So that's kind of our rule essentially. So where's the interface going to move? It's going to move over here. Why? More atoms are flowing in here. Planes are being destroyed here. So this side is being decreased because my planes are disappearing because the flux of the vacancies. Meanwhile, atoms are flowing over here. We're adding extra half planes. This plane is expanding, so my interface is going to move in this direction, from left to right. We've already talked about where planes are created, where are they destroyed. Atomistically, again, it's because of these extra half planes that are kind of being added atoms here, and meanwhile here, vacancies are kind of killing these extra half planes there. I leave the material in the furnace 100 C for 15 minutes. Where will Kirkendall pores form? They won't form because that's not long enough. But if we were to basically leave this at really, really high temperatures for long times, they would form in the hafnium region because that's where the vacancies are flowing. Great, excellent. So my application actually requires 10 to the 11th V particles per meter squared on my HF side. And I measured the density versus penetration depth on the HF side, and I obtained the plot flow. What is the activation energy of V? So I'm looking at the activation energy, and I need, let's see, it said I need 10 to the 11th V particles per meter cubed. So I have centimeter cubed. So cm to the minus 3, I know that's 10 to the minus 2. So how can I convert Cm to the minus 3 to m to the minus 3. So if I do that, that should be times, basically, I want to convert that, 1 inverse cubic centimeter, so it should be 1 times 10 to the 6th. So if I do that, so 11 would be, for 6, it'd be right here. So this is 17, so 10 to the minus 6, so that would give me that value there. So 1 inverse cubic centimeter, so that would give me this value right here. So that should give me an inverse cubic centimeter. So now, excellent, because that is basically, again, I'm going to convert that. So it's going to be this 10 to the minus 2, and then again it's cubed, so it's minus 6. So 10 to the minus 6. So take 10 to the minus 17, or 10 to the 17 times 10 to the minus 6. Give me that value. So I need this concentration. So what I'm giving it is a plot of depth versus dopant density, and then I have some temperatures and diffusion time. So I'm going to use my, basically my engineering approximation here. So x equals 2 root dt. So this is my engineering approximation here. This is my depth. We're given some different times, and we're given basically this diffusion in. So I could go ahead and calculate, and I also know that my diffusivity is d naught exponential minus qa divided by t. So I could use this expression given a distance, given a time, solve for d, and then plug that back into this equation to solve for my activation energy of B. So when I do that, thinking. So I'm going to pick some distances that look nice. So for example, I like this distance right here, because if I draw a line here, that's basically 0.1. So here my distance is equal to 0.15, call this micrometers. And I'm going to also pick this time, or this condition here. Actually, I don't want to pick that one. I'm going to pick this condition here, because that's about 0.5 micrometers. So I have got, let's open this up here. I have got my x1 distance equals 0.15 times 10 to the minus 6. My x2 distance is equal to 0.5 times 10 to the minus 6. So I could find and actually solve now for the diffusivity. So I need to solve for x1. Actually, I'm going to call t1. My time one there is for 30 minutes. So 30 times 60. 30 minutes, 60 seconds. We want everything in our good units. And then my other plot was for 20 minutes. So T2 is 20 times 60. So I've got T1, I've got T2. I need to solve x1 equals 2 square root of d. D, I'm going to call this d at, actually we'll just leave it as this. It's T1. So we'll solve there. We'll also solve for the diffusivity for x2 t times d2. So this is my diffusivity, d at 840 C, and then we have that particular value. And then this is my diffusivity value. This is at d at 940. So now I've got my equation for diff equals d naught times exponential minus qa, and then I'm going to define my k is equal to 1.38 times 10 to the minus 23. So qa divided by k times t. So let's go ahead and let's start to solve. So I need to solve. I know that my diff, set that equal to, and actually my diffusivity is equal to my D840, but then D840C. So I need to then slash dot, and I need to put parentheses around this. So I'm going to substitute it in here, but this temperature was done at 840 C, so 840 plus 273, because I need everything in Kelvin. 840. And then I also have the following equation. Same equation, but now I'm going to do, my other temperature was 940. And then D of 940. I don't know why I put the C there. So those are my two equations. I have two unknowns, D naught, QA. Give me the reals. Oops. Let's solve for that. Let's do a numerical solve. Ooh, let's see. Something is slash dot. Slash dot is replaced. And voila! We've got the activation energy. So that is basically it for problem number 3. Good luck on the exam. We'll get to number 4 next video, and I'll see you then. Thanks.